I am Uttam. I am faculty here at assistant typicality. Okay. So it's little bit informal because I'm also part of the so I don't know what else to say. But thank you for the opportunity. And we will talk about the problem of finite from trees. Prepare some outline or something so we go along. And I will spend more on the motivation than result because result can be presented on one slide. So let's start. And I start with the puzzle of thermalization and this is my understanding. Because the literature is huge and I'm only I like and what I understand. The question is that we know that from experiments that if you have a body system, always know that if dynamics is reversible, but systems react toward thermalized gives a state of okay, that cannot come because of the dynamics. This is the observation and how to explain this? So in textbook, the explanation is pretty simple and very convincing that you talk about past. So you have, and instead of looking at the system, I look at the subsystem and argue from various principles, path is large and so on. This subsystem looks good. So this is very textbook and it's very understandable. But actually the question is just different. So now you must talk about local system plus closed system as a whole, and then answer the same question. And this has been explained, and the answer is classical system. It is very successful and explains why the system was thermalized. And the backbone is the ergodic hypothesis, which I am stating for you. It's just that if you take a surface on a phase space, the system, and the hypothesis says that the trajectory will eventually to all points on it. Surface, I guess, like a trajectory there. And how many points are on the surface? The trajectory will start from somewhere and eventually come, pass to all points. And this is too, so you can relax it. It has been relaxed. Not saying that passing through all points, and it's good enough. Okay. So I might not say that it passes through all points. It's too strong and it's still at various dynamical systems. So you just say that it comes to all points and still you get excitement. Or you can talk about more familiar in text. You just talk about time and region of a constant energy and take this, then also get the hypothesis. This could prove an equivalent in this, but it doesn't matter whether it starts from here or here. To conclude, it is still the time average equal to ensemble. And this is a consequence of a hypothesis, and it's not a dynamically rule. This is still hypothesis. And this is satisfied that various dynamical work is still a hypothesis. You have to tell that you have the then ergodic hypothesis, and hence you can apply that.
Situations where it's like some systems you can do.
Yeah, like very many systems you can prove. Only few you can prove. And so this is just the ergodic hypothesis. Statement is still not there because by statement we mean we start from the distribution. So this just tells you time averages and ensemble averages are, but ensemble average over what? So what is the distribution for the trajectories over which you will average? So there comes Boltzmann's theorem, which says that you define a quantity, define a function of distribution. So f is the distribution of the space points. Quantity he called h, which is the negative of entropy. And it was observed that this function is decreases, or in other words, in familiar language, the entropy of the distribution. In fact, then you can still you can drop this observed time everywhere. Just say that with high probability this is observed, and still it's enough. And then you can say that the equilibrium state once for it is ds by dt is 0 or entropy. So this is whole concept of stat map, why it works, what was the thing. Right. If you have a question, I will.
Thermal, like, is it ground state?
An example of thermal state is G, but the thermal state thermal and ground state. In fact, ground state ground state is already thermal state at ground.
Thermal state, when you be ready.
Yeah.
And then you just say that just to make sure I'm following that from the equation. So you're saying this the stage theorem follows if you assume about the
Yeah, as long as I have to think, you can actually
no extra.
no. So all the answers are in ergodic hypothesis. That is a dynamical assumption, it's a critical thing. So ergodic theory was developed much later. So now we know the hypothesis. This came even again. But before that, he assumed something which is turned out to be ergodic hypothesis and explained out. So yes, is before.
But there is this entry on the constant energy surface. So aren't we assuming that we are going to max some quantity like entropy, then the will be thermal state?
I exactly said that. The hypothesis only tells you that time is, but ensemble, what is the ensemble? From mode thing, which is the you have to optimize this, and then the distribution that is 0 is the Gibbs distribution. Or the
Like when you mentioned that statement, I thought like that statement itself confused that the state.
No, that just tells you that each point is visited.
So all the points of constant energy will be visited the surface, but one of them will eventually be connected.
No. The distribution doesn't say that. Distribution says that each point will have certain probability. It's not selecting. Selecting, you are associating a probability which will be coming from this.
So the ergodic hypothesis is more fundamental than the second law.
Yes, because StatMech will give you all your other thermodynamics and ergodic hypothesis will mean that stat you get everything, but then everything hinges on ergodic hypothesis. So now, like these theorems were before, but you have quantum mechanics and quantum StatMech was also developed, and it was also the quantum systems, these things that they also apply. So of course, naturally you can ask for of quantum ergodicity, and this one is very difficult because as you can notice, ergodicity is not a dynamics. It doesn't talk about observable or is not observable. It's a full thing that you have to talk about dynamics. The one statement that I wrote, or you talk about Poincaré theorem and so on. Both are all are dynamical statements. Don't talk about states. They are true for the dynamics than what is the So ergodicity, the paper started from 1929 from Van who said that he had a quantum. So the previous, the H statement that was called Boltzmann, then in Quantum, he already wrote that there is a quantum. After that, there was like first. So I just saw for historical context. Yeah. So then after some time, this is 37 years. They thought that whatever Van Neumann assumed is not needed. Okay. So he assumed a lot of things, saying that the energy levels has to largely degenerate, large degree of freedom. So degeneracy is also a problem here. And he still said that without even degenerate. So he assumed something. Right? That means that if the system satisfies that property, then only they will follow a theorem. Then he just weakened. This means the ergodic hypothesis is more quantum system.
I have a dumb question. So, quantum velocity is speaking to imply about is exactly.
Because there is no failure, right? So you have to talk about uncertainties. So the fact that You can imagine a steady state point in quantum case and associate extra uncertainty. And then, of course, you can do semi-classical analysis and think. But it's not clear that what's with the underlying assumption. It is possible that you start from somewhere else and still go to classic. So this is that one paper I couldn't find that what it is. They thought both are not needed. I can rely on the third assumption that was there. Still, their theorem will follow, which means that the ergodic hypothesis is vacuous. It's true everywhere. However, fundamental presented, the ergodic hypothesis is true everywhere, so this must be wrong. That the theorem that they are proving is too weak that all the systems, normalized or not, they follow ergodic hypothesis. So this means that these are very clearly written. So, like I said, that theory was built later on. There was no quantitative notion of what is the recursive in a dynamics and so on. Came by not much later. They are like still quantitative statements, very plausible, trying to follow the Lindblad's S theorem. There were problems. So this is a criteria of situation where I claim I have a theorem, you claim no, this is wrong. And then, okay, I improve your thing. This happened. So the consensus was that if it was too general or too different, because if this was too general, I put more different. Then it becomes too restricted. No system is ergodic. So this was the dynamic there. But it's 1991. 91, the same person, but now they are thinking that okay, so in quantum mechanics you observe everything, right? So maybe a good notion should involve observable. So instead of talking about say a state becoming thermal or not thermal, they are just saying that I will actually tell later on that we just talk about observable averages. So if the average of observable becomes thermal, then I will say that this is ergodic hypothesis for me, and then I will when this will follow. And this is 94 where the term is first coined that you thermalization hypothesis with Weiss paper. And okay.
I have a very stupid question. I think it's very fully understanding. So you're saying that hypothesis is that in classical setting that all points are
Yeah. Statement is yes.
great. So is there a notion of how long you spend to each point, or because
Yeah, so those questions were there when the STM was developed. They came after quantum mechanics. They came in 1940s. So you know that it kind of is happening through experiments, but you don't know the bound. Quantitative bounds came later. That what is the time you will visit your trajectory, come close to it, or high probability statement and so on.
but when you say that the timer was on sample early, that is the distribution only on sample good is very close.
Can you say again? So I did.
So you made the correspondence that
Yeah.
the average whatever
Yes, sir.
sample
Yeah.
same time that was moving on the funds in space.
Right.
But the way that has actually depend on how much
Yes. So it will. The S theorem gives the statement, right? So this means that you will compare against the S and the ensemble against this got from S theorem. That is there, and I said the statement is weaker than I stated. So you will the correspondence with high probability with certain error. So then from time average with high probability with error. And that error will be quantified by how close you are coming to the each point. So if everything holds without probabilistic, without error, then this equivalence will be exact. Otherwise, it's high probability and low error state. So this is classical as well. Because at that time it was not known.
Because in quantum mechanics, there is defined dynamics in a timer.
Yes. But you will be surprised that like back there was a paper on quantum who were talking about the scaling of recurrence time for a dynamical system. So it's not settled in quantum that Like you know that these spectral gaps and so on.
Gaps of gaps. Yeah. So this I
So isn't quantity recursion sets the Barham time as well? How much time?
Yeah, okay, in 1940, I think that the ergodic theory Poincaré they came much later. The statement was made much before. So you know, Boltzmann was around 80. So this is the kind of history you can read from the papers. Uh, Here, because they of different, so maybe better it's a good to ask what could thermalization mean. Okay, so this is how I see. So I will divide thermalization into three parts. The first part will just ask that can you identify the equilibrium state, just like it's identified the equilibrium state, and that was irrespective of the ergodic hypothesis. It is true when the ergodic hypothesis is true, but here you want to state that you want it is standalone true. So identify equilibrium when talking about what is exemplar and what is time, because this will be the against which you will be computing everything. And this has been studied. So, for example, you are asking what are thermal states, and the answer can be given by many approaches. So, one of the really famous one is the maximum entropy. And this is a variational approach which says that why you should optimize my entropy and get the state equilibrium state. The other one is which is axiomatic in nature. It says that states are uh, equilibrium state if you cannot extract answer from it, even if you have many copies. Okay. These questions are not dynamical in nature. They are just trying to ask the equilibrium state, and there are more than one way to answer that. So you can say that I start from some variational principle and I will justify it why I am doing it. And whatever I get, I will call that those are equilibrium state. And maximum entropy principle gives you the gives. Similarly, I can say that okay, this doesn't seem operational enough to. Let's talk about axiomatic things and talk about things which we can. So you talk about complete passivity, which says states from which you cannot extract any word, even if you are given infinitely many copies. Then the state that fall into that category, I will call them equilibrium. This also gives you gives.
Is the equilibrium normally means that there's no force. So how do I calculate information?
Yeah, exactly. So that is what I'm saying. That you are identifying equilibrium state and you are arguing to be the case. So, for example, this maximum entropy principle of James, it was about information. That you say that if you are given certain information, so my best assumption, what can you make about it? Then you entropy. Similarly, another thing where about force, I'm talking about work. I'm saying that I consider it to be equilibrium state if they are useless in the sense of expansion. So it would be surprising or might not be very nice if you get states which are not, say, thermal states or Gibbs states. But it so happens that under this condition also, the states that are being singled out are the Gibbs. So this means the axiomatic approach, which was more about the structure of states. So it was not about information, it was about the structure of state so that they become useful for expression. You can come up with more and define your state accordingly.
Basically, like mean like time evolution or change or repetition of them.
This is independent at this moment and you will be able to sell if you don't connect. So I can define them on its own, but if I get something other than state, then I will have to go ahead and justify with dynamics that okay, no matter you are getting new state, but my dynamics is giving me this, it must be the notion of equilibrium. Like I'm saying that if you have say open systems, you do steady states, okay, will you call them equilibrium state or not? Then you have to justify it. So you have a dynamic gives you a steady time. So like you are invariant. Will you call them a thermodynamical equilibrium state? Then you have to bring something there. You bring experiment there, or you bring some operational thing there. But it's possible. That is why I'm putting in this category so that you don't get confused when I say thermalization. We have to understand which kind of question they are answering. So all of them are thermalization results, but they are identifying equilibrium without talking dynamic.
So for the work action part, you have to then define. It feels a bit circular because they have to define the whole theory first, right? And then
Yeah, you have to define what. If you're not saving any dynamical thing, you have to have a notion of what, and that is all you need. So, I mean, in thermodynamics also, thermodynamics you need to define what. It doesn't give you a definition of. But this is much smaller because I just talked about some notion and I need to make connection with the observation that we. The second question is again, once you know what are equilibrium state from any of these principles, then you ask that how do you get this structure? So you ask this instead of saying that you are saying talking about ergodic hypothesis or dynamic, just so that your subsystem somehow reduced to the state that you get here in the first. This is a question, and in this question there are two things here. So the canonical difficulty which I will talk and ETH I will talk, they fall into this category, which tells you that why beliefs state become certain kind of structure, and that is defined here. You want to generalize Gibson symbol, or another thing. These things answer that. Yeah, general. So they're under thermalization, but in fact they can answer any sort of question that you can decide here. That whatever whatever the special state that you get here, the second answer that why the local subsystem should go to this special state. If you are getting thermal state there, then you ask that why the reduced state canonical difficulty and ETH. This is still dynamical in the nature that I'm not talking. I'm talking about what I suppose on the states so that the reduced state becomes the state. And third question is experimental.
so what do you mean by like what answer are we providing space?
So suppose you take a global state and properties on it. Equilibrium state is defined. You have now a global state of any system, and then you constraint for it. Say that this belongs to this class, and then the region will be this class. So you have to say why you took the class, but class is the imposition. That is why you are getting an equilibrium state. You have to argue separately that why the class is relevant, but it means that state satisfying certain will equilibrium. That is what you will get here.
Do we, when we do this separation between subsystems, so do we assume it's structured on the rest of the system? Like that should be thermal or not?
No, that restriction is not there. That is why it's no thermal bath here. You have a system, but you are talking about the other part you are not talking about. You have to, of course, but not thermal.
And we imposing the condition on the global system.
Third one is very easy to state because here you just look for anything, look at experimental dynamics and see what you are getting. All of these things have been done, and the plain notion of thermodynamics, where if I divide, then I know that what kind of answer I'm getting, and I'm focusing on the second part.
So how do you go on what do you mean by dynamics? I guess you say thermodynamics is
The dynamics of the system, dynamic. Oh, Hamiltonian dynamics. Right, dynamics. Yes. For dynamics, and you have to argue that dynamics is such that whenever you singled out in question 2, so you are like I'm saying that you are saying that certain global states will reduce to thermal state. the dynamics will have the global structure that you assume. The dynamics is giving that. Otherwise, you will be standalone. It might not be useful.
So why is this the right way to take a big system class and you take a subsystem? Like, why is
You need it at some point of time because you know that if you pure state, you will remain pure. And these states, the state that are established, these are pure states. So you need to put it somehow. And entire will be put from ignoring the bar. So now I don't want to talk about bar because all the assumptions are in the bar. Bar is large, it has finite capacity. So a lot of things go into black hole. So you don't know really why this is happening. So I want to get rid of the bar and have the whole system. And then this is one mechanism to introduce irreversibility. One can come up with other things.
so what is the university? It's just looking at some system. Why is that relevant? Like also look at it.
But you are the reduced state of the global state.
Yeah. Why is that relevant?
Because the unit dynamics are not going to give you there is a partial case involved. So this is not a unit dynamics anymore.
Saying
Yes, yeah. Because then I will not look at you subsystem. I will not look at what happened. This is the question that I understand that I'm not talking about dynamics here. I am telling the structure that I want to impose so that I get variables. So here I don't talk about the two things that I wrote. And, right. So the ergodicity that is being discussed before is written like this. That you don't talk about dynamics, you just take an initial states, observe the average of variable A, and take time. And if this time average is equal to microcanonical average, so I also assume that this psi has energy. So this condition is true. You say the system quantum ergodicity. This is the starting point. This is a definition. Quantum ergodicity will only mean this. Explanation I will. In EPS papers, they are like that.
So there is this expectation over psi, and there is time of it. What is that psi? That is the like
That is that any instant of time the time. So you have say eigenstate of Hamiltonian, it will evolve. But each time you perform measurement, take time.
Quality.
nothing.
That will be too good, right? So I'm happy with proving that they are close. And this is the condition, okay? You can put a very strict condition here, right? So the first years, which shows that okay. So they start with this is my definition of when it is true, it is true, then I have snapper. And this is the hypothesis which later on Solberg said that if your system is having a quantum state, various conjecture, then ETS has to be. Again, so ETS just says that this is true. Now you have to argue that why this is true. So suddenly various conjecture in the dynamics is true, then ETS and various conjecture can be simply. It says that functions. So you have a quantum state functions. We have like random Gaussian amplitude. It's true if you're giving a state in which they are randomizing amplitudes and phases, ETH will be true. And then you have your quantum ergodicity. And then you can show that the various conjecture will be true if dynamics is chaotic. Everything is classical. So not everything, I mean this chaotic dynamics is classical. You have to talk about quantum chaos here. But it that these classical systems will give you the chaotic systems will give you plane waves which satisfy very you are hoping that your quantum system, classical thing is, then that will satisfy the conjecture and you have and written in terms of sense. Is this. Yeah. So you have eigenstates of Hamiltonian which are M, and then a psi at time t kind of expression. And there is conjecture that this Cm and e to the minus I et. These are all the Gaussian distributed. Which M is random and also random Gaussian. And this only happens if H is right? Otherwise, EM is fixed. If H is random, then EM becomes solely Cm. And that is the case, you can compute even without taking time of that, you will conclude that this is canonical evidence.
So this always, so where does Bayes conjecture come in here? Because what you
6% is true if I start with like eigen is superposition of eigen. Bayes says that this Cm is random and EM is also random. If it is not random, then you get this expression and it's not equal to the canonical evidence. If you apply Bayes conjecture, then this some term will drop here, the term will drop, and this C square will give you gives.
so you need these ordinal terms to that's the
Yes, and you want a mechanism.
The chaotic dynamics, what is the difference?
So chaotic dynamics. The easiest way. So quantum chaos. If I have a quantum system, I don't have a definition for quantum chaos. Chaotic will mean that forgets its initial computed through Lia. But again, okay. So if you have random Hamiltonian, see so that you start from this state and then it will satisfy the notion of forgetting the initial condition and diverging from it. So your question was what is chaotic Hamiltonian, right? So chaotic Hamiltonian will be defined by a property like diverging from small tiny difference in the beginning, and that you can quantify. I'm giving you an example, random Hamiltonian of sort. The condition that I
think the upper is
right.
very looking about
Right.
what are the parameters should I take this?
So using same classical Hamiltonian and find out for which parameter range is chaotic. So you have a Hamiltonian and you tell me what parameter range is chaotic dynamics because it's not always chaotic, right? So in some you have classical Hamiltonian dynamics. Figure out what are the parameters where dynamics is chaotic.
Yeah.
Then you quantize that Hamiltonian, keep parameter ranges and see what happens.
So that's what you mean by chaotic.
Yes, so classical chaotic, and then I need to do something. I mean, this is just the analogy. That is how people try to define chaos. That is why there is an exponent in quantum case. But I will say
Bayes conjecture must be a clean state.
Bayes conjecture is stated for classical quantum systems, and you again do the same thing and expect that you have to prove whatever condition that I have chaotic dynamics, I have to become random. Okay. Yes. There is I mean, you from ETL and forget everything, okay. Then there is no dynamics. It's a structure of it. Bring dynamics, then you run into another conjecture. Then the question is Bayes conjecture too. So Bayes conjecture is also a structure. It's just a or random. But to get it from dynamics, some randomness somewhere. And here I think time everywhere. There's already an ensemble here. That is how you get canonical evidence.
Bayes conjecture is true, is that still a conjecture?
No. This is a conjecture and classically true for that is no.
But Uttam, if you the time average of this,
Right.
then you don't need to worry about that because the infinity disappear.
That you have to prove. It's not random dynamics, right?
because you get if you integrate, like if you do 1 over t0 to t, you will get this en minus en.
Yeah, and you have to make sure that
Large enough time you can show.
no, you have to make
that's
sure
the-
that they're not adding. Okay, so they just phases, right? If you have and time will not give you zero.
If it makes a positive, then maybe it helps.
No, as long as I have structure and somehow some EM and EM has that this factor goes away, then you have contributions. To get these things zero, if this is random, then the phasor will cancel. Terms will cancel. You have to make sure they are random and very exactly telling you that these phasors are random. So if you take it, goes to or you can come up with some dynamics where it is going to zero. It's completely fine. The statement is very general. It says that you have to get rid of these terms, and various conjecture is one that giving you zero without going into special dynamics.
Right.
Also, the separation between those ID parts can also be when the system is chaotic or if we
Sure. So the derived statement which is coming from classical, right? So classical, you have to diverge if you difference in the then you quantize Hamiltonian and talk about say level expression. So level expression will behave in certain way for chaotic system, another way for other system. Right. So of course, this is happy thing that there is conjecture implies this, but you have other examples like systems the localization. For them, satisfy this condition, so will be violated there.
which one would be when
The hypothesis, this hypothesis. These are not chaotic. But any integrable system will violate this condition when we have one of. And as you can see, this doesn't care about Hamiltonian, what is what. This is a statement about states. That if you have some symmetry problem, how just say that if the having certain property and observer also having certain property. So this statement is true for state observable, right? So you have certain states or certain observables, and if the observable level is microcanonical level, then you say it satisfied. So this is a statement, right? So then again that your single system is like giving you microcanonical level. The idea is always the same. You want systems and O can also appear. So that's that. And then about it even simpler and even general, it is canonical. And this follows the internet and it's very simple here that you have a fixed energy system and plus rest. So you have a global. And then the statement says very simple that almost all pure that the state of system is approximately fine. So this is a statement of canonical typicality. Canonical typicality says that you take a pure space, fixed energy state, and then the state becomes approximately finite. And Harlan gives you that. So if your system is fixed from a Harlan symbol, then canonical typicality will be true, and you still get thermal state. And this is actually a much stronger statement sense. Here, what it's saying that the marginal at S, if it is thermal state, like by epsilon, then the probability is exponentially small. If you remember the previous statement, it was about expectation value of an observable. Okay? That was not talking about state, that was talking about some of the incoming thermal. Here, this is a stronger statement about state itself. Then, of course, all the averages will also be close to thermal effect.
D is what? The size of the system or some dimension?
Is the dimension and epsilon is the error, so I didn't want to write the expression here. So I just know that this is positive. So no. Generally it will scale as d by epsilon by d square or something. So this is the example. And this was the paper. I mean, just wanted to show that because we got the paper was saying quantum stat mech from entanglement. Okay. So a very provocative title that they are saying that you don't need ergodic hypothesis, you don't need anything, you need entanglement.
Is that the moment?
Yes, yes. So now let me summarize so that, like I said, I will start with time. Okay? So it doesn't matter. I like telling me results are pretty simple. So if I then ETH is like requires some chaos, notion of dynamic chaos, it is still a problem for quantum. Or you need to know that when various convexity is satisfied or have random interactions and so on. And then you might have to take time averaging, you might have to take time averaging depending on what is your Hamiltonian. But the explanation is actually very poor in some sense that you are just talking about observable things. It can tell you that some expectation values are close to thermalization, which is good enough. So this like prevailed in the community, but the observable that you observe are the only meaningful thing to do. They become thermalization. They are talking about what is the equilibrium state, and that is why for the name ET, saying that each eigenstate itself behaves as a thermal, which is like very big statement. It's a pure state. You are saying that it's a thermal, close to thermal. Only in terms of expectation values, and I don't have any problem with that. I just am guessing that this statement is not true at the state level. The second is true at the state level, and it requires hard randomness is also not a big problem. The only thing is that this statement is probabilistic in nature. It says that with probability the state becomes close to thermal state. Looking at this is not a statement, this is not a statement, and this is not a deterministic. So what I want is that hope is that I want to have a deterministic statement which is true at state level. So this is my contribution. That we want to like take some conditional states and talk about it and tell a deterministic way to show that the state is thermal. So this is kind of my motivation that I want to remove probabilistic and the observable thing. Second motivation is not well posed, but I will still go ahead with some people are here. And I'll just say that this motivation has some complexity, which I'm interested at least. And this Sandra and others are also interested. So here I'm just making a statement which has been proven that if you have a dynamical system and ask that whether some observable, the average sum observable reaches the microcanonical average or not. So you want to computationally in a way that is, then you can prove that problem is the space complete. To decide average canonical average is the space complete problem. This is case thing. Of course, what you are doing it is ETH. Okay, so you are just checking whether ETH is true or not, and this problem is complete. And this is done last year.
So the first case, I guess you mean changing Hamiltonian.
Yes. So you have to like go towards Hamiltonian inverse kind of dynamics where you will have this case. And this I wrote for like presenting HRI, so you know that it's harder than BQ will be harder than BQ. So it's pretty hard. But what else is known is that so this is I mean this is standalone statement not related to this. So these are known from this paper that not these things. This piece has come from this paper, and then I'm making another statement about symmetries. This tangential statement. That symmetries are easier to check, and in fact there are problems which you can solve that in BQP or BQP compute. And this is
That's it. James Wilson. Yeah, James.
oh, this yeah, I don't know the name. I know Brooks' name. So these are coming from Finetti-type. These papers that he took. He talked about thing Hamiltonian symmetry, and he showed that some problems are complete there for some symmetry. I had like first now like 7 papers or something. I'm just taking symmetry. So it's a nice thing. Uh, this makes me happy that I want to talk about symmetry and computers. Why if I want to check ETS, this is a hard problem. If I just look at symmetry, then check symmetry is easy. So whatever I'm thinking can work. Might be not only simpler as a proxy in some ways. This I haven't formulated. I mean, the questions I haven't formulated. So now, like my work is that I want to decide the global condition on the state so that I get thermal state. I'm talking about some symmetric state and what symmetry I will say. Then I'm believing that the global system under energy preserving unity of the which is so a closed system by definition will be energy preserving. So a closed system, so they will follow the dynamics and dynamics given by some energy preserving unity. There are more than one for a given energy. And if you believe that you cannot differentiate between these unitaries which are energy preserving, then your state will be like so. Actually, evolution was given by u to u dagger, but if I say okay, I have uncertainty about u, path on zero, then the state is that you instead of knowing exactly what you know is that there will be some u and there will be some measure on it. So this is a hard measure, but full unitary. This is a hard measure on set of energy preserving unity, which are a strict set of total unity. But this is still a hard measure because this is a product. And one can show that these states are inward. This is collection of all states which are preserving, which are invariant under all energy preserving. This is important for us. So I just let you see a little bit that collection of states which are invariant under all energy preserving units, not one. This is a very restrictive class. And then this is my result that there's an N-qudit system whose is still invariant under all energy preserving units, meaning that it comes to a set. Then any k-qudit margin, as long as k less than the square root n, if I compute a margin, then this becomes a thermal state. And you can see that this is not define a definite energy. So all the energy states are invariant. So you can take energy state, they will also be invariant. So these states don't have definite energy. You don't have a single completed unit. But as soon as you have energy for the state in the beginning, then this beta is thermal state and this mu d beta is some measure on the set of complete.
So you have no dynamics nothing. Just you take it's look at the marginals of the
Yeah, and that I emphasized in the beginning that this is not me only. So the middle portion is like that. You find a structure on the state and hope that the fate of marginals they are becoming I think it is. I'm just getting different conditions so that I get rid of certain problems that in that part of the landscape. So rest is tutorial. So if you take an energy cell here, then if you take then you get a single thermal. So I just drew some very small subsystem. You can see that the marginal is actually very close to thermal state. Single thermal state. If I take it. So this will be preparation for to this, and we have some time, so I can go through them. But I can so result I will have that okay. The contribution is not an informal result. We have to prove their amount. So that is the main portion, and this will be preparing you for that, and because I have time. So and I will also in this way that what are the conditions that I am importing. First of all, I am not taking an system. talking about dynamics, first of all, there's no dynamics there. I will talk about this. And I'm thinking that the system head off is non-interactive. Total Hamilton is sum of local Hamilton. And local are say diagonal in some basis. So X I'm taking a constitutional like this, but it doesn't matter, okay? And here I'm not putting any structure, so it can have any sort of structure. So this is total, and I told you already. These three things I told you. This you can prove very easily that this set is compact, convex, and you can easily get optimal points. So like optimal points are just the strings, their total energy. So these are maximally mixed on the subset basically. Because is not I'm not taking energy to be integer, okay? So you have to sum EX, see what kind of distinct energy is. You take it and those states the extremal point of this set. So there will be many extremal points. Except ground state, every other extremal is mixed state. The extremal state this set are not pure state, and that will depend on the density. Right, and here I want to tell you that target derivative is still non-determinate. Each Ex is different. So no 2x, no 2e, sorry, yeah, so Ex is different for different X. Right. So this is simplified, this concept it will become a little bit flipping. So
This is a non-interacting.
yes.
So why is it non-interacting if you have X? Okay, because X is
I think
what is X exactly? Is
yeah.
is particle or
So I think they just confusion. So the K is telling you the number. So H1 is a S2 second system. So we are low.
systems?
You have N systems, either of them are local. There is no just that H1 tells the identity plus H2 is I mean they don't have any fraction. Which means that there is no extensor Y kind of.
What is that?
X is some basis. You can take computational basis. Matter.
So taking out qubits.
Yes.
11
Qubits.
qubits instead of
Yes. Yeah.
K,
So,
K
okay.
non-interacting qubits.
Yeah, yeah. So K like this systems. Yes. So yeah. So here we just we say this. Maybe it's better to slow example. I just take this example. So first of all, just I mean it was not needed, but global energy is just the collection of all the answers. So it's because I took the G eigenbasis as X. So and system is non-interacting, so these are the eigenstates. Its energy will be E of x1 plus E of x2 and so on. String is an energy eigenstate. And then like I'm like taking example together as well. So take Hamiltonian like this. So this is single side Hamiltonian. Hamilton 0, 1, 2. So this means my symbol chi has 0, 2 in there. And I take equal to 3. So I have 3 qubits. And then I some sort of this thing that I have 3 sides, x1, x2, x3, and I'm just counting how many zeros are there, how many ones are there, how many twos are there. So the string is made from the character card, which can take 1, 0, 1, 2. How many zeros are there in length 3? How many ones are there? So suppose this is the example. So 0 appears 1, appears 0 times, and 2 appears twice. So the strings will like this. 0, 2, 0, 2, 0, 2. They all have the same property that all three strings, the number of zeros, number of ones, number of twos are the same. These are type. So here that you are given a sequence X, then you can define the sequence type of the sequence will be given by this empirical distribution that just count the number of 0, 1, 2, 3. That will give you one type. Set of all types. Set of all types. So you take all the strings of side such that the type is the same. So for example, if here this type P was here, then the class will be just a collection of these strings. And for this, I will even count that has energy 0, 1 has energy 1, and energy 2, so total energy is 4.
So if you have some state,
Yeah.
that also can write down in terms, right?
You can write as long as you are like this, and I mean, actually it doesn't matter. You can always write in terms of types because it has nothing to do with quantum classical or like your physical. This is just a math thing. As long as you have symbols to define them, as long as you can say that your states will be described by words, then you can also divide in type, whether it is meaningful or. And in fact, you can have other types that here 0 times 1 appears twice, here once. So you have type class corresponding to like 1, 1, 2, 2, 1, 1. And this also, if you are trying to figure out energy, so there are more than one type associated with each type class. So energy, for example, here is associated with two types, P and Q, whose type classes are having this three energy. So here are small observations that the states with the state class have the same energy. The energy was given by the number 1 and 2s, and is actually enumerating that. Also different types. So this is another known fact which I was saying about that you have a alphabet, then the type classes part of them. So you can label your states using type classes. And the number of strings in a type class corresponding to P is a multinomial distribution. I need to select these many things of them in the object. Then because each type class has same energies, selecting all the types such that they respond to energy by and the number of strings in SC. So this is not height of this set. This is number of strings in SC. It just sum of the size of all type classes. Not so these are some things that will keep on appearing. And TP will appear, SC will appear, and so on.
So just to make sure that I'm following the notation.
Yeah.
So when you read your capital,
Capital.
and not in this way, because I haven't told you.
Yes.
It was like sum over HK.
Right.
So it just adds a little way with identity.
I also assume that.
Because otherwise there's no reason the first point will be.
I agree. Yeah. So the union is not only non-interacting, they are non-interacting, they are identical as well. So I have identical N-qudits, and that are not interacting. Sorry, I said. Now, so I already showed you in some side that the extremal state corresponding to energy E is just the equal mixture of all the strings such that they correspond to energy E. Type classes, so I want to write that the state of energy E, for instance, can mixture over type class corresponding to P as long as P belongs to this. So like I said, you know my types, and then the extremal state becomes mixture of type classes. So this is a mixture of all strings belonging to type class P, and type class P has energy by N. So I sum the type class, all the types correspond to energy, and this is the state of all the will follow. So I will have a state which is mixture of all strings where this new VP is normal polynomial. Okay. Now the proof is ready. Now we are coming close, so I am very happy. So
But I want you to not get up in this. So in the previous slides, I was thinking of something else. So what do you mean by extreme state?
yes, so I had assets SC somewhere, right? This is SC of type and yes, so as I said, right, this is S, which are invariant energy-conserving unitaries. And then this is a convex and compact set, an extremal point of this set. And the
Like you can't expect
right, I assume that I assume that there is no other possibility here, so extremal would mean
definition.
yes, yes. I was confused with some other notion of function.
Yeah, I wasn't sure. I forgot like what the extreme set that you are.
Right. So this set of all energy preserving EPU invariant state. This is a compact set and extremal states. So these are extremal states. So arbitrary this set will be the mixture of these extremal states. To worry too much about arbitrary, I can make statements about extremal states. That's the idea. That is why worry. What I achieved with this type was that is very appealing. Which is that the extremal states, instead of writing them as mixture or strings, I can club them based on types. Yes. The nice thing here is that this probability that is appearing very amenable object. This is
How do you write the reference say that this object is an extreme for this figure?
you have to prove. So because I know the proof is easy, because since I know the extremal state, then I can prove it. So I will not be able to write anything other state any of these in terms of other states. That I can prove easily. If I don't know the extremal state, then the proofs are usually much harder.
Oh, you're saying that it's easy to verify that the state is extremal than to find.
No. Now since I know the answer, I can make a formal proof out of it. But if I give you an arbitrary compact extremal point, it's usually a very difficult problem. I mean, yeah.
So your set SE is like
So now this is set. This set is a set of types. So there was a SH with a set of this S set of types.
yes, but nevertheless, let's say SA, it's like a restricted kind of random space.
You could say that. Yeah.
Yeah.
I mean, you could say that. So you have a random state, but they are not equivalent. So you have a hard random state, and then you restrict it to energy-conserving surface. Okay, derive the same thing. So yeah, it's
For random states, you can express the, but there's, I don't know if these are the but you can write random states in terms of the type classes and you can.
yes. So I don't think thing here. So this so for this SH is a restriction set of all states onto to some subset of it, right?
Yes.
And I'm thinking that both are compact. So you can like pull back the hard to here, get everything same. So especially also that if you had hard random state, you have type classes there, then will automatically land you. But I didn't do that. So this was very beautiful thing because the probability that was appearing was a known fact. So that was something that we deal with many times from condensed model colleges. That of course the Stirling approximation thing that we know that is true for the binomials and so on. We are in the known territory. So actually what I'm interested in, the marginal of this extremal state, and extremal because this space now is X. So if I have of input is extreme smaller than this number. So if we can bound this, we can bound arbitrary. Bound this. And in doing some tricky business here that instead of bounding this difference, I'm adding and subtracting something which I know very well. So I define a state which is mixture over a type, a single type. Take a copy of it and take a take a mixture with respect to the probabilities UVP. He was appearing in the distribution of extreme. I take this state and mix it with mu, and then I can add and subtract and apply triangle inequality. So I into two pieces. I wanted to solve this. I can solve this part and this we get a bound. And very interestingly, the first no. Okay, so this part written like quantum state actually asking a classical probability question. You can find that this reduces to finding the total variation between two probability distributions which you are sampling with and without replacement. So this thing is and this is without replacement. So you have n and you're picking k out of them. If you like do it with replacement,
Yes.
then you get this part. Without replacement, then you get this part. This is so. And for that, like existing definite theorems, so these are these results, they show that here, but they prove that the total variation between distribution with sampling, with replacement and without replacement is just 2kd by n. So k was the object you were picking from out of n object, and these are the values they were taking. This was first finite theorem. This was done by Dicon. Right? I didn't know what is this part that how to be this. That you have a mixture of very simple diagonal states. These PIs are rationals. These are the states I by n. And this there is the so this is our contribution. So we solved all this part. So we just solved this. That this part was already known. So focus on this part. And I'll just see. Mu VP is just the ratio of multiplied by the sum. So this is a normal thing. This actually.
It's just balls and bins, right? Like,
Okay, exactly. Huh? So writing in type helps you in this because everything is integer now. So you can do those. This is very simple thing. You apply Stirling approximation here. You had this multinomial, right? So multinomial you can take log and of n factorial. Apply Stirling approximation, but we are talking about the errors here. So I apply some obvious refinement. This tells me that the leading and the remaining is 1 by n. Just practice. Once you do that, then you consider a ball. Okay. This ball is such that I know P. I know P beta. Okay. So P beta is the maximizer of sin of P. So this P beta is known. And then I'm taking like a ball who's sinking in n. Then I have a ball such that between any x, P beta is scaled a little bit better than 1 over s. If I increase it, and in this, I can expand this entropy. So there, I can expand this HP in around HP beta. Sorry, I expand HP around P beta. So I will add HP minus beta plus P beta and do this expansion. So the first time is HP beta, second time right here. So this is Taylor expansion. This is Taylor expansion of HP to P beta, and this ball is needed. Because Taylor expansion is not varied everywhere. Okay. So to have a valid Taylor expansion, I am expanding around this ball only. Because in this ball, I am controlling the error. And then my question that I want to solve becomes like a very simple statement that you sum over some polynomial here times something Gaussian on p beta, and the sum becomes over the SE set intersection with this ball. Because I did this particular thing outside ball, I will prove contributions are exponentially small, so I can stick inside the ball. So all the expressions becomes like kind of ratio. So this is sum over some sides, but they are intersecting with the ball. So remember this E was actually integer kind this kind of a thing, but it's real. So this is an S3 object. But the good thing is that these have Gaussian summand there. Okay. Once Gaussian summand appears, that is why you could prove that outside the other contribute nothing. And you can see that they are here, right? So that is why I chose a ball such that this exponential minus something survives. So that for large and small. So
Answer the denominator becomes too small.
denominator is
I'm asking you said you're going to neglect solutions that the sum that's already
so this will so these are leading contributions. Be exponentially small term in denominator values, but this term will be there.
it doesn't vanish in whatever.
This will not vanish. The problem is this will never vanish. This is just a Gaussian. It will always have one. So denominator is never zero, but once that you drop, it will go out of this. So then you cannot write like.
So this expression is exactly the non-difference that you want to calculate.
You have to like massage that expression as well to get to these polynomials. That was not big deal because some of physics they were that we are not mathematicians, right? So I took a ball because one expression was correct. Everything else, everything is so nicely sitting there. And what remains is that to solve this sums that there is a Poisson summation formula that if you have some function fk, which is now not a lattice here that we have to massage it. On lattice, if you sum some function, then this sum is actually summing on another lattice. Now these are Fourier transform. So if xi is Fourier transform, this Fourier transform is an operator. You are summing over this side. I can like and get a lattice here. But that will still not be able to be computed, but Poisson summation formula will now these Gaussian integrals for me. That's all, right? So everything is Gaussian. And so on, but thing. And we have Powell's theorem, and after that, I don't need to. I'm just saying it slowly, so you have some.
Sorry to interrupt. So the discretization is coming because of what? Because of all that you have taken?
Discretization was because of types.
Or
So types, that is why type helps. Otherwise, you could have started with definition of states. So I written in terms of mixture. I wrote normalization as a real number. I think in terms of type gives you some that is discrete. Yeah. So I take some invariant state, and let me just say state is such that remember that I approximated the polynomial as e to the n times entropy. That's deterministic. So I'm taking this state where this is not a ground state. So n is not a ground state. And it does not have maximum energy as well. So it's not a ground state, it's not highest state. Right. So I have some equivalent state, I have equivalent thermal state, and then saying that for any program, there exists of k-qubit thermal states such that for large and k is small square root n, we have this here. Trace of rho n minus k rho n, which is invariant. So this is one non-negative, this is case not. The thermal state is just bounded by this quantity. When you see the terms like the first term is like k square d times 2n, so d is fixed. First term is like k square by 2n. Other one is like k by n, 1 by n. The worst is by n, that is why I had to explain the state square. You have to something about beta. We are mu beta is a part of the theorem, so this beta is distribution, which will depend on the result is step dependent, right? So for any state I this, and what will change is mu d beta. See some constant. So this is like the part that I didn't tell you that the contribution that are coming, I that they are smaller than k square by n. And I didn't compute that. I know that there will be like above it. However, it I just dumped from this will be something that is greater than that is minus 3 by 2 plus c delta, whereas c delta actually such that I didn't write here. The c delta is such that this thing is little bit faster than n to the minus 1. This you have to insert, but if you want to do better, then you actually tell what delta and c you should do. Remember the delta was I choose a ball which has radius my n to plus delta. So delta was chosen by me. And you have to choose that this term is decaying rapidly. That is good. Oh, I got it. Delta goes to 1. So I will actually not tell everything. I will stop and go to the. Oh no, I don't need to go to the space. There again, I just want to stop. I want to this side. So because we are talking big things, maybe those things can stay no minutes. That is I'm out of the room. So initially we talk big, so that I don't know. So what I'm getting is not a okay, it's a mixture of these, okay? And that makes sense because fixed energy, because the temperature corresponds to energy. So if it has narrow energy band, for example, the initial state is concentrated around some energy, then you will get Gibbs state as well. The d mu beta will also confound that beta, which will correspond to energy of the convergence is actually by n, and so Nicola is an author, and classical definitive which is k by n. He was trying to push me that it's k by n. Okay, basically bad. So we have all, and I'm not sure if it can be improved, but one can. And this is the validity region that you have. Not only you have the EPU invariance, you have to fix the larger than square root n. So if you like trace only, then you are not gonna get this error. Okay, you will get worse. So yeah, I'll stop here.